almost everyone knows about photovoltaics, but few people know about CSP. So my effort this afternoon will be that you take a couple of clear ideas home about this technology. So I will introduce very briefly the technology itself, because maybe you are not familiar with. I will talk to you about the commercial deployment right now, which there is a commercial deployment. I will try to give some explanations on the strengths and weaknesses of this technology. I will talk about the efforts in Europe, R&D efforts to overcome these weaknesses, and I will go to the conclusions. So we are using mirrors with a parabolic or spherical shape. So we collect direct radiation, not the global, only direct radiation, and we use large surfaces of mirrors to concentrate it into a smaller area. So the energy density increases, and we can heat fluids up to 1000 degrees if we want. So most of the thermal cycles, like Rankine or Brighton, are running around 500 degrees C, the Stirling around 800 degrees C. So we can heat a fluid up to be able to run the typical power cycles, like a fossil fuel power plant. All we do is to replace the boiler. So the main application we have been seeing is electricity generation with the CSP plants. But what we generate basically is thermal energy. Now I will give you a couple of examples later on of application as directly as thermal energy. This is the scheme. We use an optical concentrator. We apply the energy to a receiver. There a fluid is heated up. Then the interesting thing is that we can choose to store a part of this thermal energy to be used later at our will. As we will see later, this is the main advantage so far of this technology, what we call the dispatchability. So there are 4 different configurations available in the market. Central receiver, parabolic trough, which is the 95% of the power, the installed capacity around the world. Linear Fresnel. I have seen a couple of good presentations about linear Fresnel activity here in Morocco this morning. And dish Stirling. Always doing the same. Use mirrors, follow the sun, concentrate, and produce electricity. This is the way a parabolic trough looks like. If you want to track the sun perfectly, you need to track in 2 axes, according to 2 degrees of freedom. This system only tracks on 1 axis, so it's not perfect, but has a reasonable efficiency. This device has an optical to thermal efficiency around 60 to 70%. This is the most common system. This is the way a commercial plant looks like. You have many rows where a thermal fluid, typically a synthetic oil, is running through the line, is being heated up, and then all the rows deliver hot thermal oil to a head pipeline. This is a central receiver system. In this system, the mirrors track the sun in 2 axes, so in principle, the tracking is better, and so the efficiency is. So these systems are the next step in the market, as I will show later, because they can reach higher temperatures, and the thermal cycle can go to higher efficiencies. Linear Fresnel. The receiver is static, is fixed, doesn't move. Only those mirrors near the ground are moving. And this is the cheapest configuration to build, but it has also the lowest efficiency. So we have to balance between both things. And the British Sterling, which is exactly the opposite, is the most expensive investment, but has also the highest efficiency, has the record efficiency for CSP systems. This is the engine. So this is typical parabolic trough plant. The synthetic oil transfers the energy to water, steam, and then it goes to run a Rankine cycle. The only innovation that has been introduced for these systems is the storage system using molten salts. It's a very stable, very cheap, and is the main tool for CSP to prevail. New systems, new developments are trying to go to direct steam generation, which means to generate the steam directly at the solar field, not to use this oil, but run the water directly through the solar field, heat it up, evaporate, and go to the turbine. So I have to say, and I said, 95% of the power around the world for CSP is parabolic trough. Problem is that, as you see in the pictures, almost all the plants are copies one of each other. No way for innovation, for different reasons. For power tower, they are lagging behind, but now they are gaining momentum. They started, the Spanish company Abengoa started with saturated steam receivers, as you see in the picture, very conservative design. Then an American company went to pressurized air, which goes for a higher efficiency, superheated steam. So this is the big brother of these prototypes. This plant is in Mojave Desert and is online since year 2013 with 377 megawatt electric power. This is really a milestone. Using superheated steam, as I said. But there are also receivers working with molten salts directly. Remember, I told you the molten salts are being used as thermal energy storage. So there is another line of work where the molten salts are directly heated at the receiver, then you can store or you can run the turbine directly. So as I said, power tower is the next step. The technology is more mature now and you can reach higher efficiencies. So this is a table taken from the CSP Today Global Tracker 2016 with the projects already under development. One of them is Noor, the third, right here in Morocco. For the Stirling dishes, well, as I said, they are the most efficient. These are small units, but for today, only 2 small plants of 1.5 megawatt are in operation. Here you see. And linear Fresnel, well, remember I said it's the least efficient system, but also the technological complexity is lower and is finding his niche in the market because can be used also for solar thermal applications, you know, dryers, and in the range below 200 degrees C, for instance, for industries, paper industry, many things. Here you see some already existing commercial plants. Now they are reaching a total of 425 megawatt, which is relevant. So what is the commercial deployment? Is it marginal? Is it to be marginal forever or what? Well, I have to say that the total power around the world is some 5 gigawatt. And it has been advancing in jumps, in waves, following, how to say, specific subsidies in specific countries. The first wave was in the US, where 354 megawatt were installed in the last years of last century. And then in Spain, following, again, a very ambitious subsidies feed-in tariff scheme. So 2,300 megawatt were installed and nothing from them. It's over. So now activity is restarting again in other countries with subsidy here, feed-in tariff there, solar park there, step by step, which I think is the right way, because they are very big investments. And we need to be very careful step by step. So here you have a list of countries that are actively supporting CSP. And I will give a few data about them. First of all, I would like to say that here in the MENA countries, since 2011, there are three plants which are not purely CSP, but are what they call integrated solar combined cycle system, which means we have a conventional power plant with gas turbine and steam turbine, and we use, in this case, World Bank funds to install an additional solar field for the power you see there, to provide additional steam to the system. So it's a good way to see, to have experience for these countries, to have experience in running such a plants, to capacity building, to see how they perform, etc. So they are there since 2011. And well, I have classified the countries in different categories. The best ones are the champions. Morocco is a champion, of course. They are developing the Noor complex in Ouarzazate for a total of 500 megawatt, 3 huge power plants. Here you see the picture of one. And to be operational by 2018. All these data have been taken from this report, the REN 21 Renewables 2016 Global Report. I really suggest you to have a look into this report, because it's very comprehensive with a lot of information, very useful data. South Africa is also running, and the driving force there is the governmental Renewable Energy Independent Power Producer Program. But it's a program, it's going little steps. They do rounds. They call for 200 megawatt round to finance, to subsidize. Then the companies apply, and the best offer wins and receives the tariff. So they have plans for the coming years up to 400 megawatt. Of course, the largest plants I show you are in the US. Again, here every different state have different subsidies and very different policies, but the largest plants around the world are there. And China. China is not a particularly good country in terms of solar radiation available. Only this region in the western side, by the way, all these nice maps are available at the Solar GIS website, which is a company doing this kind of work. And this is the map for direct normal irradiance, not the global, it's direct. So you see this area on the western side where they plan to deploy over 1 gigawatt as kind of pilot projects, which is nice. And also they are betting on research. They have this facility here where they have parabolic trough, tower, everything. This is a very clear bet. So there are many other countries working on this step by step, different scales, like Argentina, India, Chile, Israel, Algeria. United Arab Emirates have a 1 gigawatt solar park, and they just launched 200 megawatt of tower power tower technology, which is very nice. Then Namibia and Saudi Arabia also have very, very ambitious plans. Okay, I will not. You remember I said it's not only about electricity. I found, to prepare this presentation, 2 commercial applications. This is what they call enhanced oil recovery, which is to inject steam underground to ease the extraction of oil. So there is a company doing this with a solar field. I think it's better here. They put this solar field into a greenhouse to protect the field from the wind and from the dust. This plant is in Oman. And as there is no wind, the structure of the system can be enlightened, and it's cheaper, and it works. It works. This is one application, and this is another one I found. There is this Aalborg company who installed this tower system into a greenhouse tomato production facility in the middle of nowhere in the Australian desert. So the facility, the solar facility, produces heat, produces electricity, and produces desalinated water. So 3 products with this facility. Just to give you some ideas. So, strengths and weaknesses. I'm sure you have some ideas about what is wrong about CSP. I will go to that. But there is also a good side. Well, it's about steel, concrete, and glass. I mean, probably in terms of technology, it's lower than PV, for instance. So many countries can allow themselves to develop this technology. And construction and operation need a lot of people. People can find jobs. Not the guys in the picture, probably, because they have better jobs, I think. This is a joke. But, well, I'm sure you can get a lot of jobs in your countries. As I said before, the thermal energy can be stored. This is the main advantage in front of other renewables. You may decide, you can help the grid operator want to produce and want to not to produce electricity. So you give room for other renewables to be there. Because if the other renewables fail, then you can generate and fill the gap. Can be integrated with a conventional power plant, if you like. And the most important, I have to insist on this, the total capacity in the world is 5 gigawatts. I will show you a slide later on about PV, and you will see that CSP has still a lot of potential to decrease the costs. Well, very quickly, the investment cost for the thermal energy storage is now around $30 per kilowatt hour. Probably could be decreased down to 20. And the next step is phase change materials. Now go to the bad side. Sensitive to dust soiling as PV, for instance. Okay, that's true. We have to fight. And the weakest point is the need of cooling water. Because finally, it's like a fossil fuel plant. The fossil fuel plant has a device like the one shown here, where you need to cool the final water, the final temperature of the water in the condenser. And this is a lot of water consumption. Another thing is that only direct radiation is useful, not global. And as I said, the LCOE, you know, the cost of generating electricity per kilowatt hour is higher so far. This is the way they are trying to mitigate the water need using dry cooling. Yeah, I would like to, as I told you, we use only the direct, okay? So the picture there is showing the direct, the global, and the diffuse. If you have a clear sky, the direct is the green line, you see, is the highest. But if you go to one of these countries, maybe you have a day like the one shown in the picture, the satellite picture, then you have hazy sky. It's not cloudy, it's just hazy. But what happens? The NI goes down, the diffuse increases, the global keeps their curve, their values, so PV will continue working, but CSP not. So this is something that teaches an idea to us. Only go to very good places with very good DNI resource. Don't play with this. You need over 2,000 kilowatt per square meter and year. Otherwise, you are losing your time and your money. But fortunately, as you will see in the pictures, there are plenty of places like that. Concerning the price, look, this is the learning curve of photovoltaics. Maybe you cannot see it very well, but the date is that today the price is less than $1 per watt peak. Less than $1. The last offer for the Al Maktoum solar park in Emirates is less than $3 per kilowatt hour to build a PV plant. For CSP, actually, there is almost no values because there is no market. There hasn't been any market. The only reference I could find is this 12 to 16 cents of euro per kilowatt hour in the report of Stella, because there is no market. Okay? Why? Look, these are photovoltaics data. The total capacity deployed is 242 gigawatts around the world. And for the wind is 400. We are still at the first 5 gigawatts. So the message here is give us a chance. Give us a chance to evolve and to learn and to come to cheaper prices. You cannot compare. You cannot compare. There is some activity, okay, step by step. We are not in a hurry around the world. Okay, I'm coming to the research. Europe, what's going on? You know, Europe has the Horizon 2020 framework program for research. Within this umbrella, there is the Strategic Energy Technology Plan, which intends to be a global initiative in Europe between the member states and the European Commission. What to do all together in the coming years, because you know Europe is highly dependent on external energy, fossil fuels, coal, whatever. So there is already this document that you can download from the internet, which is towards a roadmap. Then for the research, there is a leg of this set plan, which is the ERA, European Energy Research Alliance, which is a volunteer association of partners, but with a very, very ambitious target, which is to put together in what they call joint programs, put together all research partners working on a specific technology. It's volunteering. It's not, no one is paying for being there. But we all know that this way, if you are there, the European Commission will listen to you and will shape the funding programs according to what you say. They don't want to talk to 20 different interlocutors to decide what to do with the money. So these interlocutors have to go together, coordinate themselves, elaborate their roadmaps, their strategic plans, and then talk to the Commission face to face. And this is what is going on. Very briefly, just to give you an idea of what's going on the research, all these are projects that you can Google because they all have their own website if you want to learn about the partners, about the work packages, the strategy, whatever. For me, the most important is stage. Stage is, how to say, is the transfiguration of the joint program of CSP into a funded project by the European Commission. It got 10 million euro from the Commission to work in these activities of coordination, improving infrastructures, coordination, technology transfer to the industry, but also to make research in all these topics you can see on the right side. But this is just, well, one more thing. We have a lot of international cooperation partners, which means all countries, non-European countries that somehow are involved. Remember the picture of China? These people is involved in stage. People from Saudi Arabia, people from Mexico, Morocco. So it's an open scheme. Everyone working on CSP can join, can apply and join. There's no money there, but at least you are playing the Premier League, if you know what I mean. STS, I think we are not good in time right now. We are finishing, no? STS is dealing with, remember, well, I didn't mention actually. CSP follow the rule of the bigger the better. Why? Because finally you deliver this steam, this solar steam goes to a turbine. And turbines are machines that the bigger they are, the higher the efficiency. And then the higher the efficiency of the whole facility. So they are not systems for a 5 megawatt or local systems, at least for now. So there is initiatives like this trying to go to a smaller scale using linear Fresnel to adapt to public buildings, commercial malls, and things like that. Remember, I told you the water consumption is a big problem, so there are two big projects, remember, several million euro. WASCOP, trying to reduce water at this cooling part of the cycle, but also for the cleaning of the mirrors. And mean water CSP. So there are two projects running on very similar topics. As I said, you can Google them, you will find them very easily and get more information. Just to say that, for instance, Morocco is involved, most of them, but other countries like Egypt or Jordan are also involved. Preflex, working with the molten salts, solar resource prediction and assessment, ORC, again with the linear Fresnel going to lower temperatures. Capture intends to improve the efficiency of power technology, power tower. Remember I told you is the next step, the next generation technology. And well, let me come to my conclusions. So we've been walking a winding road since the early 90s, but we cannot give up because there is a social, environmental concern about renewables and all these things Professor Paua mentioned before me. So we have new impetus. There are many countries now trying to develop the technology, and I think there is a place under the sun for CSP. There are, as I said, pros and cons. Most outstanding pro is the dispatchability, is where we are grabbing to not to get sunk. And the worst is water consumption, and you see there are projects with many million trying to mitigate the problem. There is some commercial deployment. Anyway, many countries, we have our niche, maybe not only for electricity, but for thermal energy, we should also look in that direction. And the R&D framework has the EuroSunMed project that has a workshop today in this building. There is a strong framework in Europe trying to mitigate these drawbacks. So again, let's give CSP an opportunity, and thank you for listening.